Welcome to the Explainer. Picture this, it's April 1970, right? The Apollo 13 spacecraft is 200,000 miles away from Earth when the absolute worst happens. An oxygen tank explodes. It severely damages the spacecraft, and suddenly, the lives of 3 astronauts are in immediate, catastrophic peril. The whole world is watching, literally holding its breath. But back on Earth, something genuinely incredible was unfolding. NASA engineers had to figure out how to bring this crew home using equipment that was fundamentally broken, and they couldn't exactly just guess. They needed a way to test their solutions before sending those commands all the way up into space. So what did they do? They turned to a physical simulator right here on Earth.
So how exactly did NASA pull this off from 200,000 miles away? Well, we have to look at their ground control approach. NASA used highly accurate physical replicas of the Apollo spacecraft. They actually used these physical models to test out various rescue scenarios, running through intense procedures to see what would work and, crucially, what would fail, all without risking the actual crew up in space. And you know what? They successfully identified a viable solution and guided those astronauts safely back home. It was an astonishing triumph of engineering. But what no one really realized at the time was that this specific method, using a perfect replica to safely test scenarios for a remote physical asset, well, it planted the conceptual seed for an entirely new technological revolution.
This whole concept evolved pretty steadily into the digital age. It started with those physical NASA simulators back in the 1960s. Then, fast forward to 1991, and the idea took a major theoretical leap when computer scientist David Gelernter published a book called Mirror Worlds. He was already anticipating a future where software models could perfectly reflect our physical reality. By 2002, this framework was officially formalized. Dr. Michael Greaves introduced the concept as part of a product lifecycle management approach, basically tying a physical product directly to a virtual counterpart. And finally, in 2010, the official term was born. That's when NASA engineer John Vickers coined the exact phrase digital twin in a technology roadmap.
Section 1. Defining the digital twin.
Okay, let's cut through the corporate marketing fluff for a second, because we need a strict, objective definition here. A digital twin is a computational model of a real-world physical product, system, or process that continuously uses real data to dynamically synchronize with its physical counterpart. Now, the absolutely crucial word there is continuously. A true digital twin must have an ongoing, live flow of real-time data from the physical asset. It's not just a static drawing, it's practically alive with data. Honestly, if a model operates without that continuous live data feed, calling it a digital twin is really just an overly broad, marketing-driven stretch.
Now, it's pretty easy to confuse this with tools we've already had for years, right? Like static 3D models or standard simulations. But here's the difference. A 3D model is really just a visual snapshot at a single point in time. And a traditional simulation? It runs predefined scenarios, but it exists entirely in the virtual world. It's a one-way street. A digital twin, on the other hand, is defined by a dynamic bidirectional data loop. It actually reacts to real-time variables, and in a lot of cases, it can even send control commands right back to the physical asset it represents. It's a real game changer.
So these twins exist on a sort of sliding scale of complexity, and we can break them down into 4 main types. First up, you have component twins. Think of this as a virtual replica of, say, a single valve in a massive oil pipeline. Step up a level, and you get asset twins. These mirror functional units made up of multiple components, like the entire drivetrain of a wind turbine. Then we reach system twins, which link multiple assets together to monitor something much larger, like an entire vehicle powertrain. And finally, we scale all the way up to process twins. These give you the broadest view possible, replicating entire workflows. We're talking end-to-end automotive manufacturing processes or even massive global supply chains.
Section 2. The mechanics of mirroring.
To really wrap our heads around how we build and operate these virtual replicas, let's walk through their life cycle. Step 1 is data collection. We equip the physical object with a whole network of sensors, Internet of Things devices, that capture real-world conditions. We're talking temperature, pressure, vibration, you name it. Step 2 is virtual modeling, where all that data gets mapped directly onto a highly accurate digital replica. Step 3 is really the magic ingredient, live integration and the feedback loop. The data flows constantly, keeping the twin totally synchronized with reality. And finally, Step 4 is analysis and simulation. Because the twin matches reality perfectly, engineers can run totally risk-free predictive analysis. They can ask what if without ever having to touch the physical asset.
Section 3. Transforming global industries.
And look, this technology has moved far beyond just aerospace. Just imagine a doctor testing a complex treatment on a personalized digital version of you before they ever write a prescription. That is actually happening in healthcare today. Meanwhile, in urban planning, geographic digital twins are pulling in 4D spatial data and live traffic feeds, which lets planners test out smart city infrastructure completely virtually. Over in manufacturing, these twins are being used for machinery crash avoidance and to pinpoint the exact moment a tool is going to wear out. And in renewable energy, they are fundamentally optimizing how we generate and store power.
To put a concrete number on that energy efficiency, systematic analysis has shown something incredible. By combining digital twins with predictive analytics in smart energy systems, like wind farms or microgrids, operators can reduce energy consumption by up to 30%. 30%! That's massive! And they pull this off through highly optimized load balancing and proactive maintenance. Basically, they're fixing problems in the virtual world long before they can cause physical grid failures.
And the financial impact of this technology? It's genuinely staggering when you apply it at scale. Take Sheremetyevo International Airport. Back in 2019, they implemented a digital twin model to forecast and plan all of their complex daily operations. Even just functioning at the pilot level, this ability to virtually run the airport and optimize their resources resulted in over $120 million in savings.
Section 4. NASA's Virtual Factory.
Now, to see the absolute bleeding edge of this technology, we really have to pivot back to where it all began. Space. Let's look at the James Webb Space Telescope. It is the most advanced space telescope ever built, literally the size of a tennis court. It had to fold up just to fit inside a rocket and then unfold out in deep space. The unfurling of its massive sun shield was this highly complex maneuver that had exactly 344 different ways to fail. No pressure, right? So, to monitor this absolutely critical deployment in real time, NASA built a specialized 3D video-based digital twin.
Which brings us perfectly to NASA's JSTAR program. They operate under an incredibly fitting motto: fail virtually, succeed actually. I absolutely love that. JSTAR develops hardware emulation digital twins. Essentially, they condense an entire flight system down to an all-software solution that you can run on a laptop or right in the cloud. By completely eliminating all those physical hardware constraints, they dramatically accelerate development timelines and vastly expand the sheer amount of testing they can do.
JSTAR basically operates as a software digital twin factory, and practically every major mission relies on a dedicated virtual platform. The massive Space Launch System, it uses a platform called Aristotle. The Roman Space Telescope uses one called WISP, and the upcoming Europa Clipper mission relies on a digital twin platform known as ECHOS. These twins act as quite literally the most valuable spacecraft components that never actually leave the Earth. Section 5. The Future of Simulation.
So what does this all mean? Where is all of this taking us? Well, right now we are watching artificial intelligence evolve digital twins from simple monitoring and testing tools into fully autonomous agents. By integrating generative AI, a digital twin doesn't just tap an engineer on the shoulder to say, hey, there's a problem. It actually predicts cascading failures across an entire network and can make long-term, multi-step decisions to self-correct the system. And it does all of this without any human intervention.
And the projected scale of this shift is just mind-blowing. Driven by widespread adoption across smart cities, aerospace, healthcare, and manufacturing, market forecasts predict the digital twin industry is going to absolutely explode. We're talking about an estimated value of $259.3 billion by the year 2032. That is a colossal industry transformation.
But perhaps the most fascinating and honestly somewhat daunting frontier here is the rise of the digital doppelganger. Developers are actually building digital twins designed to mirror human behavior and human cognition. These synthetic users can be used for training, preserving a person's legacy, or conducting user research at a massive scale. Now, while the benefits for your personalized medical treatments are enormous, it does introduce some profound psychological risks. Think about it. What actually happens when we start to believe a software model preserves our actual human identity?
Ultimately, it leaves us with this. If a digital doppelganger can continuously synchronize with your biological data to perfectly mimic your health, accurately predict your behavior, and map your cognition, where does the simulation end and reality begin?